This is the video demonstration for path planning for simple robots using soft subdivision search. In this video, we present resolution-exact algorithms for path planning. Here's an example of a path found for a disk robot in an environment with 3 polygonal obstacles. The subdivision algorithm begins by finding a free box containing the start configuration. Similarly, it finds a free box containing the goal configuration. Finally, boxes are subdivided until there is a free path from beginning to end. Here we demonstrate the subdivision process. First, the start configuration is classified as free. Then the goal configuration is classified as free. Note that green boxes are free. In this case, the subdivision proceeds in a breadth-first search. The largest boxes, still mixed, are prioritized for subdivision. This proceeds until a free path is found. Here we give the basis for the correctness of our algorithms based on resolution exactness. First, the algorithm has a constant k greater than 1 independent of the input. There are 2 conditions for the resolution exact algorithm: path and no path. In fact, for a given epsilon, if the greatest clearance is between epsilon over k and k times epsilon, the program may print either path or no path. This is an area of leeway for the program. In this clip, we illustrate these 2 conditions. For this environment, the program's output was no path, as seen in the lower right panel. If we decrease the radius of the robot from 8 to 7, then the program outputs path found and displays the path. Notice that if we keep the radius at 8 and decrease epsilon from 2 to 1, the program again outputs path found, since it is now searched with finer resolution. Our algorithm depends on a classification of boxes. Resolution exactness opens the way for a soft classification, which intuitively means that they can be implemented by numerical approximation. The classification has 3 possible outcomes: free, stuck, and mixed. Free and stuck are definitive answers, and the soft predicate is set to be conservative if it never makes a mistake when it outputs a definitive answer. The other requirement of softness is that it converges in the limit to the correct answer. This display demonstrates the classification of the boxes and their color code. Notice that boxes smaller than epsilon are colored gray. The algorithm is controlled by a priority queue which contains boxes that are mixed and greater than epsilon in width. In the main loop, we repeatedly remove a box from this queue, split it, classify the child boxes, and put the mixed boxes back into the queue. The algorithm terminates when a path is found, or if the queue becomes empty. The getNext method of the queue represents the global search strategy. We use several search strategies for the priority of the queue. Note that the choice of strategy does not affect correctness, but may affect performance. Here is a path found where the boxes were chosen using the random strategy, and typical of the random strategy, we find that most boxes have been definitively classified into green or red. This path was found using the breadth-first search strategy. Notice there are more yellow boxes and they are the same size. Finally, this path was found using the greedy best-first search strategy, which is a form of A star. In this subdivision, large boxes were left yellow, and priority was given to boxes along the line connecting the start and the goal. Notice that this strategy is the fastest of the 3 we've seen. We now look at the 2-link robot. The 2-link robot has 4 degrees of freedom, 2 spatial and 2 angular. The configuration space of the angular components is topologically a torus. The boxes visualized here are really the projection of the four-dimensional boxes to their xy coordinates. This environment consists of 8 corridors converging on a central atrium, with 3 small obstacles within the atrium. Here is the same environment, but with the random strategy selected and epsilon decreased. Notice the random strategy took 2.5 seconds. The BFS strategy took 3.1 seconds. The greedy best first strategy took only 0.7 seconds. The distance plus size strategy took 0.9 seconds. And finally, the Voronoi heuristic took 1.2 seconds. Here is another path found by the Voronoi heuristic. We also implemented a version of the two-link robot where self-crossing of the two links is forbidden. Here, theta 1 may not equal theta 2. In the torus picture, the forbidden configuration corresponds to a diagonal line. Notice that the configuration space is still connected. We can generalize this forbidden diagonal to a forbidden band around the diagonal to forbid the links from coming within a certain angle of each other. Here is a solution to the T-room environment where crossing of the links is allowed. Initially, the robot is laid out horizontally at the top of the T. And here is the solution where the two links may not come within 10 degrees of each other. Notice the robot is forced to take advantage of the bar at the top of the T.